Before we start solving some logarithmic functions, let's recall some properties that will be helpful. Remember, we had a homework where we looked at some different values of logs and noticed that when we add two logs together, it was the log of the property. When we subtracted two logs, it was the logs of the quotient, and we also saw that we could take an exponent on and off of a log like this, and they were equivalent to each other. So let's take a look at more of a formal statement of those properties. The power property, p times log base b of a, is equal to log base b of a to the p. So I can put the exponent on the number inside the log or take it off, whichever is helpful in a particular situation. I also have the product property and the quotient property. Notice that the log base has to be the same. We add two logs, it's the log of the product. Subtract two logs, it's the log of the quotient with the same base. Please do not get the quotient property mixed up with the change of base property. The change of base property says if I have log base b of a, I can rewrite that using a different log base, whichever I choose, which I just called c here, putting the number inside the log in the numerator and the number that is the base of the log in the denominator. This is the log of two things divided inside the log. This is two logs divided by each other, so they are very different. This change of base property is particularly useful if you have a calculator that does not do log bases other than natural log and common log. So you can always evaluate a log like this using common log or natural log. We also saw these properties here on a previous worksheet. We said that 5 times log base 5, let me open this up again so it's where I want it, 5 to the log base 5 of 25 is just 5 raised to the power that we would have to put on 5 in order to get 25, which is 2. And then that makes this 5 squared, which is 25. So if these two bases match, the answers match. Because this is log 10 to the log base 10 of 100, then this would just be 100. This is e to the natural log of 4, which is e to the log base e of 4, so this is just 4. This is 4 to the log base 4 of x plus 2, so this is x plus 2. Now that's going to be helpful in solving equations. So in general, b to the log base b of x is just x. We also talked about that you cannot take the log of a negative number. If you take the log of a negative number, it ends up being imaginary. If you take the log of 0, it ends up being undefined. So we have to be careful, particularly when we're solving equations, that we check our answers to make sure we're not taking the log of a negative number or 0. Okay, so let's start solving some equations. The first one is more of an example of how to exponentiate than actually something you would need help solving, probably. If you see two logs that are exactly the same, set equal to each other, then what inside obviously has to be equal to each other. So x plus 2 has to equal x squared. But I want to show what happens when we do something called exponentiating. That means we choose a base that matches the log base, and we use the two original log expressions then, or the two expressions on either side of the equation, whatever they happen to be, as exponents. Since the two bases are equal, and since the two expressions on either side of the equal sign are equal to each other, then these two expressions must be equal because they have the same exponent or equal exponents. Then, looking up here, we see log base 4 of 4 to the x plus, or 4 to the log base 4 of x plus 2 is just x plus 2. So this simplifies to x plus 2, and this simplifies to x squared. So we just end up with x plus 2 equals x squared. This happens to be a quadratic equation, which we can solve by factoring. Set it equal to 0, factor it, and we end up with two solutions. Now I said you have to be careful not to take the log of a negative number. So if we check both of these in the original equation, we see that if x is 2, we have log base 4 of 4 and log base 4 of 4, which are both equal to 1. If we put negative 1 into both sides, we have log base 4 of 1 and log base 4 of negative 1 squared, which is also 1. Log base 4 of 1 and log base 4 of 1 are both 0 because 4 to the 0 equals 1. So both of those solutions check, even though one of them is negative. All right. Now let's look at another situation where exponentiating is actually really valuable. So first of all, I want to look at solving this equation two different ways. And the first one, and I would suggest if you're writing this, watching the video, don't just sit there and copy the stuff. Actually listen to what I'm saying here, which is why I usually uncover things a little at a time. There's two ways I can start this equation, or can start solving this equation. I can rewrite this in exponential form by saying this is base 10, so 10 to the negative 2 power equals x plus 5. I could also exponentiate both sides using a base 10. I could say 10 to the log base, or 10 to log base 10 of x plus 5 equals 10 to negative 2. I end up then with x plus 5 using this property up here. End up with x plus 5 is equal to 10 to the negative 2, which I've changed to 1 over 100. I probably should have left this as 10 to the negative 2 here. So we just end up evaluating both sides. I'm stumbling over my words here. Anyway, we get the same thing on both sides. After that, all you have to do is add 5 to both sides and finish solving. When you add 5 to both sides, you get 5 plus 1 over 100, or 5 plus 0.01, 5.01. Subtracting 5 from 5.01, and back in the original equation, you have log of 0.01 equals negative 2, which means 10 to the negative 2 equals 0.01, which is a true statement because that's 1 over 100. Okay, now we're going to look at a couple problems now, actually 3, where we have multiple logs in the same equation. When you have multiple logs in the same equation, you always need to start by combining the logs into one log, and then we go from there. So we're going to use the product property to combine these two logs together, and we end up with natural log of 3x squared. Now we have two different ways to proceed from here. We can exponentiate, or we can rewrite in log form. Either way, we'll end up with the same thing. I can recognize this as log base e, so e to the first equals 3x squared. Or I can exponentiate both sides using base e. E to the natural log of 3x squared is just 3x squared, and that equals e. Once we do that, then all we have to do is divide both sides by 3 and take the square root. When you take the square root of both sides of an equation, you get both a positive and a negative solution. However, if you look back in the original problem, we can't use the negative solution because that would be taking the log of a negative number, and we would end up with imaginary numbers. I will leave it to you to check this to show that you can do this on your calculator. I'm sure you'll be fine with that part. Now let's look at another example where we have two logs, in this case subtracted. So, and we use the quotient property, which means this is log base 2 of the two arguments here divided, x plus 1 over x. I am just going to rewrite this in log form, so 2 to the negative 3 is equal to x plus 1 over x, or 1 over 2 cubed equals x plus 1 over x. Now I am going to solve this, and I'm going to go ahead and just, at this point, get rid of this and take a look at the rest of the problem. Now I want to show you kind of a step-by-step process, and then also remind you of a shortcut. If I have 1 over 8 equals x plus 1 over x, it simplifies this if I clear the fractions. So I'm multiplying both sides by 8. 8 divided by 8 is 1, leaving me with just 1 on this side. This 8 is 8 over 1, so this is 8 times x plus 1 over x. Then I can multiply both sides by x. X divided by x is 1, so this leaves me with 1 times 8 1 equals 8 times x plus 1. I'm sorry, x. I don't know why I crossed this x out. That should not have been crossed out. This should be x equals 8 times x plus 1. And then all I have to do is finish solving. And I actually kind of went the long way about finishing solving this, but anyway, get all the x's on one side and everything else on the other, and you end up with negative 8/7 for x. Now I want to show you on the calculator something interesting, and this would have also happened if you'd tried to check the previous problem. Notice that if we put in negative 8/7 for x, that we would get a log of a negative number, which we're not allowed to use. That we get imaginary solutions. So I want to show you this on the calculator. On the calculator, if I tried to check by putting negative 8/7 in for x in both sides of the equation, or in both places where there is an x, I would end up with negative 3, and here's why. Log base 2 of negative 8/7 plus 1 gives me this imaginary number, and log base 2 of negative 8/7 gives me this imaginary number. I reset my document settings so it would only show 3 decimal places, but both of these are actually longer decimal numbers than this. But I want you to notice that the imaginary part of the number is exactly the same. So if I subtracted this number minus this number, which I show in the next line, and I went ahead and changed them both to 2 decimal places so it would turn out right here. Negative 2.81 plus 4.53i minus the quantity 0.19 plus 4.53i ends up just being negative 3, because the 4.53i minus 4.53i is 0, and negative 2.81 minus 0.19 ends up being negative 3. So even though both individual numbers turn out to be imaginary, I can actually end up with a real number answer. So technically, this is a solution, but what I'd like you to say is that this is an imaginary number, so we're going to not use this solution. Okay, we have one more to go. This one has a radical in it, and we have 2 logs added together, but we cannot add these logs. We cannot combine them yet because there is a 2 on the outside of this. So this is where the power property comes in handy, moving the property back in. So we are first going to rewrite this as log of the square root of x squared, and that just becomes the log of x. Now we have the log of x plus the log of x, which now we can rewrite as the log of x times x, or the log of x squared. So we have the log of x squared equals 4. So now we can do one of 2 things. We can say 10 to the 4th equals x squared, or we can exponentiate both sides, and either way we end up with x squared equals 10 to the 4th. Then take the square root of both sides. The square root of 10 to the 4th is 10 squared, or 100, and we do plus or minus. Obviously we cannot use the minus because that would be an imaginary number, so our answer is 100. So to briefly recap, use your log properties. Remember that you can either rewrite the log equation in exponential form or exponentiate both sides in order to get the variable out where you can solve for it. And then make sure to check to see if there is a negative number in the original problem where you're taking the log of a negative number. Since that will end up with an imaginary number for the log, we're not going to use those as solutions.